Okay, let's start, and till now we discussed several issues of disconnections. In particular, we focused on the operation type, so it was disconnections or functional group interconversions to basic operation, then synthon to reagent conversion, and Umpolung operation, I mean the changes of the reactivity type of the synthons and reagent corresponding to these synthons. Today I would like to say a few words about such an operation which we will call synthon modification. So, synthon modification and once more let's take this my molecule which I say I love. It means that one. So, this derivative of carboxylic acid, which is a lovely molecule for disconnection because of this functionality, which provides here a variety of potential disconnections, a variety of potential operation in organic synthesis. So, let's say that we would like to use these synthetic schemes that we already are acquainted with, which we studied basically during our third year course. So, for example, the method for synthesis of carboxylic acids. In order to have that, we would like to have such a disconnection. So, third, we will perform a functional group interconversion to change this into a sulfate, and of course, once more we are dividing table into two different sides. By the way, now that we are equipped with a table, so it's much easier, much nicer to see that kind of appropriated way of writing the reactions or the schemes. So basically what I can observe here, that still it's not the way that we could have a lecture in a nice lecture room, but anyway it's much better than this small, very small piece of paper, sheets of paper. And of course synthon to reagent, it means that in such a synthetic approach, which is very easy, let's say that one, which could be simply oxidated by potassium permanganate, for example, or perhydrol and acetic acid, so different potential reagent or auxiliary reagent are available to perform this oxidation, and we are obtaining this target molecule. And now the second disconnection, it is just that we could realize now that we would like to have pure carboxylic acid to indicate this synthon modification, and once more, if we would like to observe the reactivity, it's that kind of disconnection. Once more interesting feature is that now we see that and we have here, of course, acceptor O12, so acceptor 2, and then a sulfide part. With this will be, of course, the donor 0 reactivity, and once more we'll see here synthon to reagent. So synthon to reagent, and this will indicate here the potential reagent. So we should, of course, have something like that with an X, where X means chlorine, bromine, and so on, and then such a thiophenol, of course, under basic condition. This provides us the carbanion, which will react in the substitution reagent to provide target molecule. Let's say we'll put here target molecule 1 to obtain target molecule 1. Now I must get rid of that what I have drawn here, so I hope everybody have an occasion to make the notes. Anyway, it is easy to stop the movie, so this makes this way of lecture even more reasonable and more practical than a real-time lecture in the lecture room. And we have now this, let's say, target molecule 2. So we now have target molecule here. We draw that. And of course, if I would like to have a pure carboxylic acid, I must perform something like umpolung, so umpolung. So we are changing the chlorine or bromine here to hydrogen, and in fact this will be something like functional group interconversion. Functional group interconversion. Yeah, so from the point of view of retrosynthetic analysis, we can discuss this in the following operation, because we have here the acceptor synthon, and we would like to have that one. So it will be simply such a synthon. And we may now ask a question: what is the reason that we would like to have such a O12D2 reactivity instead of acceptor 1? And the answer is obvious, because we know the way in which the carboxylic acids could be synthesized as the alkylation of malonites. Everybody could now go to the lecture of organic chemistry and we'll discuss that at the very end of this lecture to the course that is available on YouTube at the University of Silesia, which simply discuss that problem during our third year course to once more refresh our knowledge of that method. So, this to discuss this FGI is just that we synthon to reagent, yes, so we would like to have a synthon to reagent, and of course this could be readily into this is target molecule 2, yes, to obtain target molecule 2, and this could be easily performed using the Hell-Bolar-Zielinski reaction. So, how would HVZ reaction so simply the chlorination at the alpha carbon atom. So we have that one ready, and we have this target molecule 3. So this will be target molecule 3. And once more, I must get rid of that what I have written here. Let's see a small inspection if everybody is recorded properly here. Yeah, it goes. Yeah, it goes, so I think everything is okay. Because I'm alone here in my home office, so a problem is that so once more, put that here. It is target molecule and hydrogen, and once more we should get rid of that molecules on the right side. Yeah, and once more let's say that we make a disconnection here. My question is now, should we proceed this kind of disconnection, A, or this kind of disconnection, that is B, and let's say 0, 1, 2, so disconnection A will produce the 2 synthons, so nucleophile at the alpha position, and we well know that if we, let's take the carboxylic acid, so it is a very sensitive position, because under the attack of the base we are obtaining an enolate which could react as a nucleophile, being alkylated, for example, in the well-known malonate synthesis. So we may see now, and I will not use my time now to discuss this disconnection B, but let's go for the disconnection A. So accordingly we have something like with methyl here. Of course hydrogen is still here, so it is this methyl group, hydrogen is here, and once more target synthon to reagent, so it is simply a remark, and synthon to reagent conversion. So we will perform here this kind of chemistry. So we need such a molecule with, of course, hydrogen here and which under the influence of the base could simply obtain this kind of carbanion, which could be then alkylated by the chloride, alkyl chloride or bromide or iodide. Of course, it is the propionic acid, so this could be bought very easily, and we can see here, for example, from the Sigma Aldrich immediately that it is available, and everybody could just try to see that in the network and cannot not perform this kind of search using my phone or computer, because it's just busy performing this recording. However, let's stop for a while so I get rid of all I have written on the table now. Where is my old board equipment? Yeah, so get rid of that. Okay, I just leave that here, but this should be noted just here. I mean lower, 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 but I would like to get rid of that molecule, so I'm leaving it here. And we all know that we have such a method, so still we should keep this right side of the paper noting, so that we know that the synthesis of the carboxylic acid could be performed using the ethyl malonate, so such an ester, and by the application of the base we are obtaining such a carbanion which can react with the, for example, any kind of alkyl halide and produce such an ester, which could be then hydrolyzed. Yeah, this could be hydrolyzed, so under the the water with, let's say, an acidic condition, we are obtaining the respective carboxylic acid. Or with respective under temperature, we can have decarboxylation and just such an acid with single carboxylic group here. So we all know that kind of chemistry, and actually an option here is that we could have such a instead of ethyl malonate, we can use the malonic acid, which could be similarly alkylated by relatively novel. It is not so new, but let's say 20 years old, and we do not necessarily need here the ester, but carboxylic acid could also be used in that kind of chemistry. So let's say what we see is that let's say a started molecule, something like 3, I think, we haven't used 3, so once more disconnection here. Target molecule 3, and a disconnection here, and we will then obtain, of course, in that kind of chemistry, a minus sign, a plus sign, so this will be a hydrogen here, and D2 reactivity. And then it is, of course, acceptor alkyl. I mean, for example, methyl chloride, methyl bromide, something like that. And synthon to reagent means that we can use, let's say, X chlorine or bromine, and we have here and now we have something like synthon modification. So we have already discussed this conversion. Such a reagent or synthon to malonate, which will provide us simply very similar potential or reactivity for the alkylation. So it is, of course, D2 once more, and in the reaction of alkylation, so with such a molecule, so under the influence of the base, we are obtaining here carbanion, which then will be alkylated, and after hydrolysis and decarboxylation, we are obtaining the corresponding monocarboxylic acid, which we as analyzed here on that table. So now to finish that part, because I do not like to produce too long lectures, I'm not sure how this will look like after my inspection, everybody should come back and see once more that part of the third year course that is available on the YouTube channel at the University of Silesia for organic chemistry course, in which we are analyzing the synthesis of the carboxylic acid. As it was the course for beginners, we could understand the differences. We are using here some advanced topics, as for example malonate synthesis and so on. However, how this looks in the course for beginners. So compare this please as the topic for today's seminary. And that is the end of that part of the lecture. Thank you very much.